Okay, I have 12:20, so if you don't mind, maybe we start. Hi, Moritz. Okay. Oh.
Before the break, I would like to make one announcement about the next slots
Yes.
last week and then guided tour by German.
Oh, nice. Okay. Okay. So in the previous weeks, you heard a little bit about the aerodynamics or aerodynamic properties of the local blade of the wind turbine. And in the coming week, you're going to hear about the properties of the wake. And so I want to do a bit of a bridge lecture that tells you a bit what the wake is and why you should care about it. So before we start, first, please interrupt me if you have questions. Then the other thing is, you already know I have a bit of a problem with speaking too quickly. So if you notice that's happening, please wave at me, and I will do my best to slow down and so on. The other thing is, as I've already seen, you're sitting in the front mostly, and I really appreciate that because I think the volume will be easier to adjust that way. So let's start with this question. What is a wake? The wake is the disturbed flow that's behind an obstacle. Typically, this flow is highly turbulent, which means there's a lot of mixing going on in it. And the place that you've most likely seen the wake happening is behind, for example, obstacles in liquids. So for example, ships, because at this interface, it's a lot easier to see what's happening with the wake. In this particular case, you have a ship moving from left to right, and this white frothy region behind the ship, this is the wake. So if our obstacle is in a gas fluid, it's sometimes very difficult to see the wake, and we can't always rely on being able to visualize it. But I have a nice photo here, which you may have seen before, from the wind farm Horns Rev in Denmark, where there's enough condensation in the air of the wake that it becomes visible. And when we look at this, we see a couple things. The first thing is the wake is pretty big. It takes up pretty much the entire horizon in the previous photo. And secondly, that some of the wind turbines are directly positioned within the wakes of the previous wind turbines. So from a farm perspective, what this means is that the flow is no longer fresh when it comes to the later wind turbines. So the later wind turbines aren't receiving the free stream velocity that the first wind turbine would see. And because of this turbulent mixing in the wake, these later wind turbines, they don't get to harvest wind which has as much energy as the first turbine did. So within the farm then, later turbines will be less productive than the first ones will. But what happens to the individual wind turbine? And one thing that you're going to see next week, the argument, is that the wake really limits the amount of power that a wind turbine can harvest, just an individual, by about up to 60%. This number you'll find next week, anyway. And otherwise, it also influences the apparent velocity that shows up at the blades themselves. So clearly, this wake could have a pretty big impact on the behavior of our system, and we really want to know what it does, what it's doing, how to model it, and so on. And so this particular lecture We want to ask, what is the wake doing? We want to ask how the wake affects the wind turbine, and then to say, what could we approximately do, very conceptually, very briefly, roughly, so on, to model the wake, and then to give the practical information to find numerical details somewhere else. So when we talk about what the wake's doing, very quickly, some philosophical implications that we get from lift, then angular momentum, and last we want to look at some experiments, because pretty pictures are always nice. So let's begin with this. We have an airfoil, and this airfoil is experiencing lift and drag. We know from Newton's second law, or excuse me, the first law. Actually, anyway, we know from one of the Newton laws, sorry, that if the flow is exerting a force on the body, this aerodynamic force, that the body has to be exerting an equal and opposite reaction force on the flow, right? So if we look at the general flow as it arrives at this airfoil, and the general flow as it leaves, so on the right, we see that this mass of air has to be deflected downwards, right? So what we might do is to look at the velocity vector that it arrives and say, you know, if you step back and squint a little bit, roughly speaking, it's been rotated clockwise. Excuse me. Okay? So now I've said this word rotation, and this was not so good of me. Because rotation, when we hear this, it implies solid body rotation. So things like that, the rotational velocity is proportional to the radius from this center of rotation and so on. And that's not the case for fluids because fluids deform. So what we want to talk about now is circulation or circulatory motion as opposed to rotation. And what we've seen in this past series of pictures, of sketches really, is that any time that you have this circulating flow about a body, you also have lift on that body. And the other way around. If you have lift, you also have the circulating flow around that body because Newton's laws hold true and so on. And so these two properties, they're synonymous and they always happen together. So I want to do a little bit of a thought experiment. Let's take an airfoil, which is initially at rest within a fluid. Okay? At some particular point in time, we want to give this guy an impulse acceleration so that afterwards it has a uniform velocity. Okay. This is the impulsive start. At some future time later on, we want to do the exact opposite. We want to give this an impulse deceleration so that afterwards the airfoil returns to being at rest. Okay? Thank you. If you have a constant lift coefficient, can I ask you guys, what happens to the lift in this particular picture, sketch? Yeah, exactly. Right. So you also have this unit step up of the lift and then a unit step down exactly at this impulsive start and the impulsive stop. Okay? And now at this point, take my word for it, you'll see it a bit later. The circulation is proportional to the lift, so we have the exact same unit start and unit stop of the circulation. And now we have to remember that circulation implies this circulating motion, which implies there's angular momentum in the flow, right? Or angular momentum in the flow that's directly around the wing, right? And now I kind of feel like there might be one or two of you who are like a bit hyperventilating, because if you see at the beginning, it looks like there's no angular momentum in the flow, and at some point we've magically created some, and then it disappears again. And that doesn't really fit with what we understand of physics and the world, right? Angular momentum should be conserved in a system, right? So what part of the flow might be compensating for this change in angular momentum of the flow around the wing? Hands?
Wake.
Yes, thank you, because that's the point of this lecture. Right, so we just said that the wake is typically turbulent, right? Turbulence means mixing. Mixing implies there's this circulatory motion, so maybe that's where angular momentum is going. So let's make ourselves a nice hypothesis that the wake exists to conserve angular momentum in the flow. Okay? What would this look like in our little sketch that we said before? Okay? So we said at some certain point in time when we had the impulsive start, thank you, then at that point we need to release angular momentum into the flow in order to compensate for the angular momentum that's been won by the fluid that's immediately around the wing. Okay? So now at this point, we can see that the sum of this angular momentum and this angular momentum now sums again to 0, which is what we had initially. Okay? And then when the airfoil comes to a stop again, we have to do the same sort of counterbalancing behavior. We need to again release angular momentum into our flow, into our wake, so that then again the total angular momentum of our system is still conserved from before. Right? And since circulation is the way that we've been thinking how we get angular momentum into our flow, that means we have to be releasing some circulation into the flow at the impulse of start, and then again some other and counterbalancing amount into the flow at the impulse of stop. Right? So that's this blue dotted line here, nicely. Okay. So it's all very nice that I've made you a pretty little line sketch, but how do we know this is actually what's happening? So let's make some experiments. Okay? The first thing we want to ask is whether we actually can find anything being released into the flow or into the wake at all. Because obviously if nothing is being released into the flow, then this entire thing has been a waste of 10 minutes, right? So what we can do is to take some photos of an airfoil as it gets this impulsive start, and we can see if we find anything being released. I have for you at the bottom a little timeline, which again has the blue solid as a circulation on the wing, and the blue dotted as a circulation being released into the flow, where this red line is the velocity of the wing at time. And there's this black slider bar that you should look at to see at what point in time we're looking at for this picture. Okay, so part one, notice that there's this little like puff here. And if we advance forward in time, that puff is moving downstream, until at some point it leaves the window completely, right? So it definitely does seem like something is being released into the wake. Although, again, we don't know what this is, right? It might be a marshmallow, right? That fits the characteristics quite as well too. Okay, so the next obvious question we need to ask is the thing that we've seen being released, does this actually have circulating velocity? Does this actually have circulating motion? Because otherwise it can't possibly compensate angular momentum in the story. So what we want to do now is to take an airfoil and do this impulsive start and impulsive stop again, and watch to see what the circulation, if there is any, does. Okay. In the previous photos, you saw that the camera was moving with the wing, so it was making streaks of the wind, or of the particles in the flow. At this point, the camera is moving with the flow and not with the airfoil, so we can watch to see these streaks to see how the fluid is being dragged along with the airfoil. Okay? So we definitely see, if you can tell, that there's this like circulating pattern of velocity of the particles in the flow here, because there are these little lines where the particles have moved while the camera shutter was open. And we also see that behind the airfoil we have the exact same thing, presumably rotating the opposite direction. Right? Okay? So let's move forward a little bit in time. And you can see that this shed circulation, this guy has moved down further as it's been convected downstream. And again, we still have circulation on the flow, on the airfoil, so we must still have lift. So now let's make one more leap forward until after the impulsive stop. And at this point, oops, where am I going? Yes, thank you. At this point, we see that we still have the shed circulation that was released at the impulsive start. But now we have another little circulating motion pattern here, which is released at the stop of the airfoil. Right? And again, then we don't have any more of the circulating lines on the airfoil that happened because we had lift. Right? So far, this seems like it's matching what it is that we thought our hypothesis would show. Somewhat agreed? Okay, somewhat disagreed? Maybe you raise your hand then. Okay, right. So up till this point, we've been talking about 2D airfoils. And now the question is, like in reality, we very rarely have 2D airfoils or infinitely long airfoils. So what happens if we have a finite length airfoil? A finite length wing, excuse me. And in this case, again, we have the nice sketch. The force points upwards. This is more or less our lift. We have the circulation pointing one direction around the airfoil. And then we have the opposite direction of circulation that's been shed into the wake. Okay. If we then build in three-dimensionality into this problem, we could say that because we have lift, we have to have high pressure on the underside, or the pressure side of this airfoil, and we have to have low pressure on the upper side, or the suction side of this airfoil. And at the wingtip itself, there's no longer a barrier that's keeping these two differently pressurized regions of air from mixing with each other. So the air will try and escape, or the fluid, excuse me, will try and escape from the high pressure side to the low pressure side. And we might picture at this point that we would again get circulating motion here, right? So really in our series of questions about how this works, we should expect that if we make a little experiment, that we would be able to see this circulation trailing behind the tips of the wings, right? So to make this experiment, let's take a 3D wing, which is operating so that it has constant lift acting on it. And let's see whether we can find this circulating flow pattern behind the wingtips, okay? And I propose to you that this is exactly what we're seeing here, right? So the fluid as it comes from underneath the wing into top wraps itself around the wingtips, and then that flow pattern is shed downstream, okay? So yes, there does seem to be circulation trailing behind the wingtips, okay? But now you might say, okay, we're in a wind energy course, like we never care about what happens to wings that are just flying steady level flight. We only care what happens to rotors. So let's pin the bottom wingtip of this wing into place, and let's rotate the top one, okay? So now we have a rotor, and what we'd expect to see is that this nice set of spiraling lines, which represent the streak lines as they travel through this circulating motion, that this guy would get wrapped around in the helix where the path of the wingtip has been. And this is seen in reality. This is a case where there's been a smoke flare attached to the wingtip, to the one wingtip of a rotor, a wind turbine, and run in a large wind tunnel and lit so that you can see where the smoke goes. And while we're looking at these pretty white lines, they designate where we think that the fluid is circulating around. Okay, so we would expect to see that fluid is circulating, so has this circular motion, around these pretty white spirals and also down the inside of this helix, because that would be where we had pinned the wingtip that had previously been at the bottom. Okay? So let's see if we can find this in reality, which means, again, another little experiment. Okay? So, again, a wind turbine rotor operating in steady conditions, and let's see whether we can find this circulating flow pattern behind the tips of the blade. So here we have a nice wind turbine, a little one, and we can see that someone is injecting smoke into the air that's just past at the bottom of the rotor. Okay? And then now, very regularly patterned afterwards, we see that there is this circulating motion pattern, which would be where we would expect it to be given the nice pitch of this sort of helix, right? And in this case, I admit to you, the photograph of the turbine is really clear, but of the flow, it's a bit blurry. So maybe this is all just invented, and we should double check this with another photo, where here, the flow is very clear, but unfortunately the wind turbine itself is not so clear. So what I propose to you is this box here is the wind of the wind tunnel behind us. This here is the rotor, and we're looking horizontally at the axis of rotation that's being stretched down the axis of the wind tunnel. Right? And then again, we see that yes, at very even intervals, we get this circulating motion pattern that's being shown by the smoke as it enters our frame. Right? And again, this is consistent with what we would expect before. If we have this shed, this shed circulation pattern introduced into the wake. Okay. So what we might say now is that we've made a little bit of exploration into our hypothesis, and we might say the wake is conserving angular momentum, or it does seem to be demonstrated this way by our experiments. So are you guys convinced? Raise your hand if yes, and okay. Put your hand up if you're not convinced at this point. Okay, maybe we do you have a specific question?
It's just a little not clear.
A little bit not clear. Okay. You're right, there are a lot of pictures and there's no mathematical background behind this. At the end, I'll suggest some references you should look at if you want the mathematical background. And hopefully that helps a bit. Okay. So if we do believe that this is what's happening, then the main question we should ask is, do any of us care about this? Because obviously the wake is positioned behind the wind turbine. Maybe that means the wind turbine says cheers, and the wake goes on its own business, and the wind turbine, also gets its coffee and does what it wants. So the real question is, how does the wake affect the wind turbine? And we might look at this a bit. So again, let's see another of these combined photos and sketches. We again have smoke introduced at the wingtips, and then we can suppose that we have this circulating motion which is being carried along by the white spiral that you see everywhere. Okay, so one thing you may notice is that on a given side of the turbine wake, the circulating motion patterns, they're always oriented in the same direction. Which means that at some point, at some point you would expect that there would be some component of velocity that's kind of pushing back upstream here, right? And again, some component that's pushing downstream here, right? Just from looking at the sum of these circles, or circular motions, right? So if we enter in a uniform free stream velocity into this field, then we see that there's a velocity deficit that's getting pushed where the flow is getting pushed back upstream slightly in the inside of this wake, right? And again, this is a sketch, so not to scale so on, but you can see that near where the edges of the wake are, where you do have the circulating motion pushed inwards, you would have the velocity decreasing in the downstream direction. And then at the center of the wake, where there's none of this, there's no circulating velocity component pushing the wind back upstream again, you see that you get much faster wind again, okay? And now comes the point where we realize that we are talking about an incompressible fluid, which means there are no shock waves in this story. So if we want to get between a uniform flow and this velocity deficit, like camel type thing, that we have to have an intermediate velocity profile in the middle, right? And I feel like this might be kind of boring to you, except that you remember that power is related to velocity cubed. So any small velocity deficit here is going to have potentially a large impact on the power that we can produce, right? So now I've been talking to you about what happens on the rotor scale. What happens to the individual blade? So let's say you have your blade, which is flying nicely, or moving nicely with some apparent velocity, UA. Okay, we said that there's a circulating motion component to the velocity of the flow around this airfoil because we're producing lift. And because of this, the flow behind the airfoil has to be pushed down. This is called downwash. And it's going to induce for us a velocity that's downwards here. So if we look at what the velocity is that the airfoil actually sees, it's going to be, again, pointed slightly down. It'll be this vector sum of the apparent velocity and the induced velocity, right? Which again, looks like pretty sketches and so on, but it has a big impact because now our drag is actually parallel to the effective velocity and our lift is perpendicular to this, effective velocity and the span. So now we have some resultant force of our aerodynamic forces. And when we project that back into the apparent velocity frame, you can see that we effectively have more drag than we thought we would, and we effectively have less lift than we thought we would, right? And so this difference in drag, this is called the induced drag, and you get that like purely because you were generating lift. Like, so this is this messy explanation that I totally failed at last week, where because we get this nice property of lift, we have to pay something for it. And so some percentage of that lift that we get has to be redirected into drag, right? So ultimately, the fact that we have this wake increases the drag on the airfoil. And in and of itself, we say, okay, fine, that's a little bit tedious, but we can deal with it, except that remember that our power harvesting factor is related to CL minus CD times our tip speed ratio, which means that if we increase our drag coefficient and we effectively increase our drag coefficient and we effectively decrease our lift coefficient, then our power harvesting factor is going to go down, right? So we've definitely lost some performance here. So both in terms of the rotor having less, having this velocity deficit as the flow comes through, and also because we have to increase our drag coefficients because of the wake. Thank you. So if we've decided this is important, we now have this question, like, what do we do about it? How can we conceptually model this? And I don't really want to go into a lot of mathematical detail about the way that I propose that we can possibly model this, because you're going to hear a bit of a simplified version next week and so on. But I do want to give a bit of a framework that will include some terminology that's necessary if you go about reading the textbooks that we propose, for example, the Burton textbook. So let's play a little game. I tell you, imagine that there is an invisible state variable, and this guy travels along some structure, and because it's traveling, it has this curious property that it produces a force field, which more or less only acts on certain particles. And now I ask you, what does this sound like that you've heard of before?
Current.
Yes, thank you, exactly. This sounds like electromagnetism. Okay, so in that case, there's a current which is traveling along this conductor, the wire, and this produces an electromagnetic force field that has the property that it circulates certain particles, namely the magnetic ones are the ones that contain moving electrons. Okay, so if we say that this sort of thing already exists in real life, we might say, hey, let's just copy the structure and do the same thing for fluids, and that way we can find a way to model our circulating flow. Okay? So what we're going to do is we're going to introduce a state variable that we call the vorticity. And this state variable is conducted along structures that we call vortices, or vortex in singular. And it has the nice property that it produces a force field, the pressure field, which acts to circulate certain particles. And I mean, yes, you will see it on a table as well if the table is very light or the pressure field is very strong, but it's mostly relevant to fluid particles. Okay. We make this particular analogy because it turns out that the underlying structure of the equations that describe the motions is very similar. So in both cases, the electrostatics case and the incompressible flow case, we can describe some interesting parameter as the Poisson equation of a vector potential. And in this case, we're not interested in the current density, but we're interested in vorticity, where we've now defined vorticity to be the curl of the velocity. Okay? And if we're now going into this business of definitions, we might say, okay, let's quickly write down a formal definition of circulation, which we've been talking about all along. So circulation is defined as the flux of vorticity through a surface. Okay? And it turns out, I'm not doing the derivation here, but you can see it later, that if we've defined the circulation this way, that the lift per unit span is directly proportional now to the circulation about a body. Okay? Which is a pretty nice and cool result that it's such a simple equation. Anyway, back to our normal story. Okay. The reason that we particularly care about these Poisson equations is because we know what the solution is to them. And the fact that we have a known solution to something which is as complex as any crazy fluid that you can imagine in a domain is kind of amazing, right? The unfortunate part is that the integral is really ugly. Okay. And it's not the sort of thing that you can, in general, integrate easily analytically, and so on. But there's kind of a saving or a rescuing idea, which is called the boundary layer. And I want to go very quickly through that sort of detour to say how it is that the boundary layer actually rescues us in this case. So remember, at this point, we have a solid boundary. So there's no flow traveling through this boundary. And we know that if we go infinitely far away from this boundary, at that point we must, almost by definition, have the free stream velocity, right? But close to the boundary, so like very, very close, if you zoom in like microscopically on this surface, no matter how smooth it seems to look or feel, it's made up of microscopically these jagged edges. And even if you were a perfect machinist, you'd have to imagine that there would be atoms who are here, and the atoms themselves would make a jagged structure. Right? So fluid elements that are traveling very close to this boundary, they're going to get stuck. And if they're stuck, they can't be moving relative to the boundary. So there must be this zero relative surface velocity, and consequently, this what we call the no-slip condition. And this then gives us the nice form, with some viscous help, of the velocity profile at the boundary layer. sorry, I said too fast, of the velocity profile. Anyway, what we might do is to say, we don't really care necessarily what this thing looks like so much, as we do care that at some arbitrary height, we're going to call it delta, the boundary layer thickness, we've effectively reached what the free stream velocity is. So at delta, we have more or less like 90% or 95% or 99%, for example, of the free stream velocity. And this then delta gives us a split in our domain now. This says that any altitude above this delta, this belongs to the external flow, and you more or less already have the free stream velocity where there's no shear gradient. Okay. But below this delta, below the boundary layer thickness, you're now in another region that we call the boundary layer. And in this case, the shear gradient is strong. Like you can see that there's a very fast increase in velocity here. Right? So if we now decompose the velocities that you see in either the external flow or the boundary layer, we can decompose this into part 1, a mean term, and then part 2, a deviation term. We can see that, yes, again, there's more or less no deviation here in the external flow. But if we do that same sort of trick down here in the boundary layer, we see that there's quite a lot of this deviation here. Right? So there's this large difference between what's happening at the upper part of a fluid element and the velocity at the lower part. And this is then a large shear gradient here. And we happen nicely to know, again, I'm not explaining it here, but we happen to know that one of the ways that vorticity enters a flow is through shear gradients, viscous shear particularly. So we might say, hey, maybe up here in the external flow, the vorticity is negligible. And maybe down here, the vorticity is important. So let's make this split between the external flow and the boundary layer and separate how we treat the two. So remember, the entire point of this boundary layer discussion was because we're trying to solve this really ugly integral. And particularly, this is an integral over domain V. So now we can split this into a sum where we split the domain into 2 parts. One part is the boundary layer, and one part is the external flow. And for the boundary layer, yes, we say the vorticity is non-negligible, so we definitely have to keep the integral. But for the external flow, if the vorticity is 0, then this entire messy thing drops out, right? So now we've saved ourselves quite a lot of effort, if you're allowed to make this particular assumption. Yes. So I want to quickly look at what this sort of split does, because I think visually it makes a bigger impact than if you just see the sketch and so on. So this is a nice photo of an airfoil at a relatively low angle of attack. But it's high enough, this angle of attack, that you see that there's separated flow behind, before the trailing edge, let's say. So one thing we know is that where the flow is attached, boundary layers are typically pretty thin. Right. So when we start to separate this into our external flow in blue and our boundary layer in red, we see that we've suddenly cut our domain by a huge amount. Because now the place that we have to integrate this messy thing is really only the red part. And that seems quite nice, right? Okay, there's also one particular circumstance in which case the problem becomes even nicer. And this is why people are frequently so very happy when they say fully attached flow. And that's because at this point, the boundary layer is thin until the trailing edge, and then remains thin more or less after the wing as well. So effectively what we've done is we've dropped one dimension from our integral. So if we have here in this photo, we have a surface as our domain, then what we end up with as the new domain of our simplified integral is really only a curve. So clearly this is a big savings in the effort it takes to integrate this thing. And one thing we might do, and it brings us into this family of vortex methods that I'm not really talking about today, is we might discretize the vorticity within our domain into some summation of like elementary solutions where we know what the analytical integrals are of those, of these vortices, of these elementary solutions. And then we can stack all of these solutions up together until our boundary conditions are finally matched. So now we have this nice summation, and we've avoided the entire integrating business to begin with. Okay. So until the very last bit, and even then, there's been, I admit, very little like mathematical rigor and explanation of the physics behind this. So if you want to know that, I present to you some optional references. This stuff is not then going to be on any sort of course exam, but I think is fun and exciting, and I hope you do too. So the first thing is there's a document that's going to be posted up tonight. The plan is currently midnight-ish, which is a very short guide to vorticity and vortex methods. And I hope you like it. And then if you find that you're still interested and you think that this is like marvelously fascinating, I definitely approve of if you think, then I have two other recommendations, the book of Branlard and the book of Wu Ma Cao, in order of increasing thoroughness and rigorousness, and so on. So, at this point, thank you for paying attention to me. Any questions? Okay. Yes, thank you.
Can you go back to the induced velocity?
Yes.
Diagram? Can you again explain how the gain affects the velocity?
Sorry, one more time, a bit louder.
How the change affects the trajectory?
Yes. Okay, so
Excuse me? Maybe it's better if you would repeat the question.
thank you. Good. Okay, so the question was, if we think that this particular idea of induced velocity holds true and that this causes then an increase in induced drag, how does that particularly change with the quantity of lift that is on an airfoil? Is that the question? Okay, so one thing we said before is that the circulation is directly proportional to the lift per unit span. Okay, so right now it's just this nice little spiral, but you have to imagine that this spiral gets stronger proportionally with how much lift you're producing. Okay, and this spiral is representing how much velocity is being induced in the flow. So the stronger that this spiral is, because the stronger your lift is, the larger this particular arrow is, right, of the induced velocity. And because you have this nice triangle and your effective velocity is a summation of these two vectors, then the larger your lift is, the larger your circulation is, the larger your induced velocity is, and then the larger this induced angle of attack is. Okay? And by parallel lines, we can see that if this guy here, the apparent velocity is like parallel to the green drag according to the apparent velocity, and the effective velocity here is parallel to the purple line of the drag according to the effective velocity, this angle here between the two must also be the angle of attack, this induced angle of attack, alpha I. And since both of these lift and drag vectors together are perpendicular, we see again, this is why this is again alpha I here, right? Okay, so the larger the lift, the larger the circulation, the larger this induced velocity, the larger the induced angle of attack, and consequently the further offset, or the further you have to rotate your frame of reference according to UE from UA, right? So if you picture that this guy is, the resultant force stays the same, but the coordinates that you're projecting it onto, these guys rotate further and further. So the larger alpha I is, the further along this particular circle of the rotation is going to be moving. So if your alpha I becomes very large, then maybe your drag according to the U effective is only here, for example, in which case you have this entire amount of induced drag. Yes, thank you.
Are you just saying that the circulation makes the wind velocity shift even more?
Yes, exactly.
So then your
Yeah.
reference frame is
Shifted further. And so then if you project your resultant force back onto what you think the flow should be, because it's the apparent velocity that you calculated in your nice geometric program, you're going to be more and more wrong about how much drag you have. You have to more and more increase this induced drag component that you're carrying along. Yes, Frank?
Is this effective velocity just the velocity after it's past the wind?
Yeah. So to be entirely fair, we should be doing this at the center of pressure of the airfoil. We should be doing this more or less at a little bit behind where it is that this circulating pattern is originating about. But again, yes, it's always downwash that we are using to calculate this, so it's always downwards. Yes, Paul?
So it's not the same effective velocity in the velocity of wind. It's coming right at the...
Right.
It's not the same.
No, we were using effective velocity beforehand, I think, as our shorthand to say that there is effective velocity then coming up later. But yeah. Further questions? Okay. A 10-minute break in that case. Then we'll be back. Thank you. They're already uploaded. You can get them now. Sorry, that was still quite a lot faster than... Okay.
Okay. Yeah. So let's. You will use stay or?
If you don't mind,
Yeah,
I have one.
okay. Perfect. Yeah. So you. Good.
Slower, because I think I will.
Oh, don't worry. Perfect. So does the microphone work? Yeah. Okay. Okay. So thank you, Rachel, for introducing us into the wake and for showing beautiful pictures. I need to admit that Rachel took actually much faster than she and I predicted. So I will improvise this lecture and basically present what I would have presented to you next time. But the good thing is, because Rachel was fast, we can be slower now on the other thing, and maybe we can also use, if there's some time for questions, to answer these questions now. Before I start, actually, I wanted to make a short survey or an announcement with you. I contacted the people that operate the wind turbines on Roskopf. So as you know, Freiburg has 5, nearly 6 turbines here. And 3 of the Freiburg turbines are actually on Roskopf. You see 4 because 1 is not on Freiburg territory. But they are all operated by the same company, and the manager of that company would be willing to give us a guided tour to these turbines at our lecture times. But because it's not just a usual lecture slot, you would have to have a longer trip to go there, right? So that's why I want to announce it a bit in advance, so that you can plan for it. I think it's worth the effort. It's exciting. I'm also excited about it. And the dates that I got offers, and I need to check them, are actually, I think it's the 5th of June or the 4th of June. Let me just check it. It's one of our lecture slots. I think it's a Wednesday, but I need to check. No, it's a Tuesday. The 5th, exactly. So the 5th of June, we would be possibly going up to the Roskopf. Would you like that? I mean, we don't have to do it, yeah, but I guess you will probably like it. That's exactly what I still try to find out, and where to meet the best. I mean, June 5. It's a Tuesday, June 5. And we have an appointment at 12 o'clock on the wind turbines. So if you want to go there, and I think Google Maps can help you to find the way, but I think the best way is basically to go either by bike until you cannot bike anymore and then walk. Are there other remarks or some ideas? Yeah.
Well, you can actually bike to the top, but I mean, can you just explain what we're going to do there? We go inside the turbine?
I don't know exactly how. I mean, I said that we are 37 people. Actually, that's how many people submitted the first exercise. So I think they will not be guiding all of us up the turbine. I guess this is not so easy, right? Because there is limited capacity to move up and down. So I think they might open the turbine, and anyway, the guy is there to explain us all details, so we can definitely watch it from the outside, hopefully go inside and maybe watch some things and ask him a lot of things. Yeah. But I don't think that we will go upside, but I ask him what he usually does with these guided tours.
Roughly
Yeah.
how long do you think, how many hours will be?
Sorry?
How many hours will it take?
Yes, so that's exactly the point. I think we will probably, so we will need probably like 10:30. I think you need to have your own timing. I think something like 11:30 we could meet at some place relatively down of the turbine. And then we could walk up together, for example. I think that's maybe the nicest part. Or maybe first I should ask, who wants to go there? It will probably take like 5 hours in total. Yeah, okay. So then, who was already on Roskopf, on this Roskopf tower? So maybe, okay, nearly half of you. So what's your preferred way to go up? Just tell me, how do you usually go up? Walk. From here, more or less. Yeah. Okay, from Schwabentor to there, 1.5 hours. Perfect, great. So you have seen the turbines from close. Okay, good. Other suggestions? Walking is probably a good idea because we can also talk on the way. Other suggestions? Yeah. Exactly. That's what that's why I announced it well in advance so that you can make plannings. Yeah. Yeah. Yeah.
Isn't it possible to move to the next day, 6th of June? Then we don't have any lectures before 2. So we have
I mean, it might be different for different people to have different lectures, but that wasn't on offer. I mean, he just offered me a few slots. That one wasn't on Tuesday. I would have preferred a Wednesday as well. Mm-hmm.
So on this day we have a lot of us has a lecture.
Okay.
From 8:40 till 12.
Okay.
But we have only limited numbers of these lectures. So
Okay.
it's
Okay.
quite an exercise.
And it's only in June. It's only in June.
Yes.
Mm-hmm. So in July there wouldn't be a problem. It's every Tuesday.
Yeah.
Okay. Every Tuesday. Yeah. For all SSE students, as I understand. Okay. And it stops at 12. And if you would leave a bit earlier, like at 11?
Everybody got the exercise.
Yeah, you could, yeah. Okay, I will see if we can make our appointments a bit later so that we would actually meet this guy maybe only at 1:30, let's say. After that slot you would have time, more or less. I mean, we had a lot of conflicts after that time. That's why we moved our lecture to this time, right? But so I would try to make it a bit later so that you can leave maybe, I don't know. A bit later, and then we could meet, let's say, at 12:15 or something down at Schwabentor and then walk up together or something like this. That could be one option. Or maybe, yeah. Anyway, I tried to find out a good schedule, or maybe, yeah? Yeah, that's. I also asked already. I didn't get an answer yet on this question if we can record it. We will ask it. Yeah, but it's a different thing to record it or to go there. And to ask your questions is definitely a difference. Yeah, so I will find out more details. I just wanted you to already think about this. Tuesday, June 5. Try to keep it reserved, and in particular the afternoon after this, so that we can maybe move it a bit there. That's it. So someone else? No. Okay. So no remote participants. Okay. Good. Okay.
But the Wednesday slot is not available.
Some Wednesday slots might be, so not in that week, but I will check. Yeah. So maybe just a short question: who would prefer for this guided to a Wednesday slot? Who would prefer a Tuesday slot? It's nearly half-half, I think. Yeah. Okay. But we will try to make it. But afternoon is better than morning. Is that normal? I mean, if we lap into from 12 to 4, would that be easier than from something in the morning? Yes. Good. Yeah.
Because some of us already have a lecture on Tuesday until 12 p.m.
Yes, that's exactly what people told me.
Yeah, okay.
Yes, exactly. So basically, the question is what we do, and then I try to make it possible that you can attend this thing. Yeah. I think it's impossible to drive with a car to yeah. Okay. Yes, I will synchronize a bit more and then pre-reserve that. Yeah, notify you actually next week. Yeah, maybe before we continue, is there something to follow up? Some general questions regarding the previous lectures or the organization? If not, then I would just give you a bit of orientation. Where are we? So basically, Rachel started with what we call chapter 3 in our lecture. So 3 is aerodynamics of wind turbines. And actually, I would be grateful if one of you could write all the text that I do, because then I could make it as lecture notes this evening. Is someone anyway writing and has a nice writing? Rachel will do it? Okay, great. Yes, no, but it's perfect. Yeah. So what Rachel presented to you was what we call a view on wake. It was mostly pictures, but I think you got the main message, and the main message is the flow is slowed down because there is a wind turbine, right? So that's like the main message. And what we will now do is we will try to make from this relatively, actually maybe the other message that she conveyed to you is flow is complicated, right? I think this message has arrived for sure. It's full of very strange motions of circulation, of vorticity, and of eddies and turbulence and boundary layers, and I mean flow is not simple. We all agree on this, I think. I mean even fluid dynamicists, like people that spend their life investigating flow, no one says that flow is simple. Yeah? No one thinks that flow is simple. Flow is very complicated. But you can try to make simple models of flow, and one of these is what we call the actuator disk model. And that's what I want to start today. Actuator disk model. And this actuator disk model leads to what is called Betz limit. And so it will be an important part of this. And the Betz limit. And Betz is a scientist who was teaching actually in Göttingen, yeah, where they had one of the first aerodynamic experimental research centers in the 1920s, Göttingen in the north of Germany. And he was writing one of the first textbooks on wind energy, which I also have. It's a very thin one. And if you are able to read old German typewriting, which is Fraktur, it's not very easy to read, but it's then you will enjoy this little book. So in this book, he derived what we now call actuator disk model and his limit. Yeah? And this limit will actually tell us how much energy a wind turbine can extract from a given wind flow, and it's significantly lower than what we would get from our first estimate. As Rachel said, it's above around 60%. Okay, so I think I better close this door. It somehow disturbs my thinking. And I want to summarize basically the fact that we had already. So what we know already is that a wind turbine slows down the air. Yeah? Wind slower in and after a wind turbine. Yeah, so it's not blowing with the full velocity that we would expect originally. And this has very, very delicate implications, which we can try to understand in a relatively rough way already, using the same physics that we used until now and not using much of flow. But we assume, I mean, we know that the wind is getting slower in and after the wind turbine. And the picture for this is, and this is now an interesting thing, if you think of streamlines, right? What does it mean if air gets slowed down? I mean, just think of the following. You have a mass of people running very fast across a lawn, right? And then at some point it gets mud, yeah, and they run much slower. Yeah, the same people will run much slower. What you will see is even if everyone ran very quickly through a lawn and they ran on a thin line, yeah, once you get into the mud, this the same group of people that's still moving with the same number of people per second will get much broader, because the same number of people needs to distribute itself on the needs to go through the same number of people needs to go with a slower velocity, so they need to get thicker. That's actually, somehow the same reason why when we have a motorway and it gets into the city, then you get like a motorway has maybe 2 lanes, and then you get 4 lane or even more after that, because then the cars get slower, so they need more space. So what this means is that if you look on a side, let's do a side view on a wind turbine. So what happens here is actually that we have our wind turbine somewhere in the middle. I draw this disk here. That's now our actuation disk. It has, of course, think of it as a circle, but I see it from the side. It has an area A that we already had before. And then here I just sketch the rest of the wind turbine so that we get the idea. So that would be our wind turbine. But the rest, it doesn't matter. So this is the actuator disk. And the rest we neglect. And now the question is, what will it do with the flow? There is some velocity here. We call it u infinity, and this is I call it u0 now. Yeah? That's the undisturbed flow. Disturbed wind velocity. Then it will somehow get slower when it goes into the wind turbine. So there will be less wind here, and then there will be a slower speed behind the wind turbine. And that implies, and this is like the thing that I want you to note, it implies that there is actually air needs to slow down, and that means implicitly that it actually the part of air that passes through our turbine comes from a slightly smaller region, and then once this velocity is constant again, this region remains big again. So this is how we should imagine the flow through a wind turbine. Huh? So it's slower velocity here. I will actually use some name conventions in order to make our formulas not look too complicated. But maybe one thing I will already say is that the speed that I have here at the wind turbine, I call it u1. So here we have u1 is a slower speed. And this is slower than u0. That's an important and sad fact. Yeah? So that means that we have less speed there. Yes?
We have the same line and the same level.
Yes. So if you have more than one turbine, then of course the picture gets much more complicated, right? I mean, if you have one here and then one here and one here. And so this is not covered by what we do now. But you can already get the image. I mean, roughly speaking, I will call this U3 for a reason that becomes obvious in a minute. So this slower velocity will then be the inflow velocity of the next turbine, so to say, right? Fortunately, there is some influence from the outside air and so on. So it gets, I mean, if you go like many times the diameter of your wind turbine downstream, at some point your velocity will again be u0 because there's friction with the outside of the wind field. Yeah? And in particular, from the top, from above the boundary layer of the Earth, there is always energy coming from top down, and that actually at some point brings all the wind again to the speed. I mean, the same thing when you have a skyscraper behind it, there might be a long wake, but when you're 10 kilometers behind the skyscraper, there is nothing left, right? So you don't see it. It's lost in the general turbulence of your wind field. Okay, so somehow our coordinates, this will be a particular point, and I will need the next blackboard in order to draw what I want to draw. But maybe I already explained the big idea here. So the wind speed is a function of what I call x now. It's a length coordinate, x. Yeah, so it's just like x in meters, which is a measured distance from the actuator disk. So could be, for example, a 0 here. Yeah, that could be one way, and then this would be negative axis, and that would be positive axis. Yeah. And what I want to sketch is now the function of the velocity as a function of x. And also I would like to understand the pressure. Yeah, and then we can do computations later. So maybe the first thing is one thing that we remember. Yeah? Remember? Yeah? Just to get you, what was the power in a wind turbine in our rough estimate, if this would all not be there, right? We estimated that. We said it's okay, it's something half times rho times the area and then times the speed. Yeah, u03. And that's a power that is not achievable. Yeah. So this is like the first guess. It's not achievable. But actually it has still a name, and we could call it, I think it's the power in the air, so to say, right? So we call it the power in the air. That is in principle in the air that would flow through the actuator disk if there would be no actuator disk. So if you would just have this ring of like a hula hoop, yes, so you know these rings. So if you would just place a ring into the airfield and you would just watch the air flowing through it, then you would have this power. But because you actually need to slow down the air, you will not get that power, unfortunately. And then there's this factor that is due to Betz, which we will derive. So let's now view on the wind turbine the velocity in this direction. Yeah. So u. Maybe I should also say that I start to call velocity u now. The reason is not that Rachel used it, but the reason that Rachel used u is that in the literature people always call the velocity u. Yeah. Just get used to it. It's a wind velocity. Well, why people call it u is, yeah, there is some reason for it, but for us it's just convention. Okay, u. So what we have here is x. Its position behind the actuator disk. And so somewhere there is a 0 position. And what I have here is u of x. And u of x is actually the wind velocity in the direction, in the same direction. And of course, I talk about the wind velocity on this line somewhere. I mean, somewhere inside our stream tube. This whole thing is called a stream tube. And maybe I should just sketch it correctly. I mean, if this would be an ellipse, then of course here there would be also an ellipse. And here there would be also an ellipse. And we could imagine this whole thing as a tube. So air is flowing. It's getting a bit slower here. And then it's getting to a new speed. And very far away it would get u0 again. But anyway. So what we see is that the wind starts. And then it will go down somehow, and then it will settle to some value. And this one, I mean, this is the curve that I call u of x, right? And I already know that it will have some value u0 at the left boundary. And it will have a value that I call, and I gave it the name already, u3 at the very right. Yeah, so that's like what happens when you're infinity there or infinity here. And I reserved this because I want u1 and u2 still to exist. Here I said this is u1. But in fact, actually, I would like to stress that we will have to distinguish between before and after the disk. It turns out that in this case it's the same. Yeah, but u2 is equal to u1, but it's just before and after. So I will have, so to say, 0 is there, 1 is here, 2 is there, and 3 is when I'm over there at infinity. So this is my counting of giving indices to my quantities. Yeah. Yes?
Could you adjust the position index first?
Yes, I should have it here, right? So the 0 wasn't nice. You mean? Yeah, okay. But anyway, so 2, and this would be 0, as I said. This would be 3. And maybe I want to bring it in formulas. So u of minus infinity, so to say, is equal to u0, right, by definition. And then u at the location 0, and this is maybe the location of the wind turbine, is equal to u1, is equal to u2. And then I have u at plus infinity is equal to u3. So that's my definitions. Yes? So I don't need to adjust it, Rachel. So it's still, this would be still position 0. I mean, I could give it another name, but yeah?
After the actuation is kept infinity, wouldn't this become this?
Yes, that was my answer to your previous question, but this is not what we cover here, so to say. And the actuator disk assumes that there is, so to say, no friction between the streams tube and the rest. So there is basically, there will be other velocity with u0 that flows always here, yeah, with u0, and they will not interact because there is no friction in the air. So that's an idealized model. Yeah? So in this case, we call it u infinity for this simplified model, not for reality. Yeah? Maybe I should say this. Assume no interaction of the stream tube with the outside world. So, and this reflects reality, of course, not to infinity, but to a really large value. Maybe if you go like, usually you measure it in times the diameter, and if you go 3-4 diameters down, you will have a very close approximation of what we will have here. So this is like the first thing that I wanted to give as an idea. And of course, the velocity is something that you cannot abruptly change. I mean, even with a disk, there's air flowing through it. So we can safely assume that this U1 and U2 is the same. This will not be the case for the pressure. And that's why I introduced actually 1 and 2 as different numbers. So when we look at the pressure along the same axis, so if I have here now the same axis, position behind the wind turbine, and here's my wind turbine somewhere, then what is an actuation disk in essence? So to say, think of it as, I mean, because we know that it's rotating blades that somehow have a very strong force on this air while it flows through them. But you could also think of if you cook pasta, yeah, you put them into a sieve, and such a sieve you could think of being in the air, and so somehow this sieve will slow down the air, and it can only do so by pushing against the air. And what does it mean if something pushes against the air? There must be pressure. So there must be a pressure difference at this actuator disk, and this pressure difference must be so that there is a higher pressure before than after, because we slow down the air. So what we will have is pressure here. I mean, this is like the pressure diagram P of x. So that's pressure, yeah, and this is x.
The pressure is higher before than after, then the force will be that direction.
Yes.
But
it
has to be this direction, so we slow down.
No, sorry, the turbine itself will be pushed in that direction by the wind, and we will, exactly, the turbine will be pushed in that direction, of course, and it will push back the wind in that direction. So that's, so to say, what happens. And actually, you're right, and let me just show it to you in a minute. So actually, because our turbine gets pushed to the right, there must be a jump here at this actuation disk, a pressure jump. And interestingly, and this is now the thing where there is some interaction with the outside, I mean, the pressure cannot be, I mean, different when you're very far up there or there is the outside pressure. I mean, when you stand next to a wind turbine, there is no pressure difference. Otherwise, there would be air flowing around the wind turbine all the time. You see, otherwise there would be extra wind generated by it. It's not. So what we will have is here is P0. Yeah? P0 is what I could call P at minus infinity. Then there is one pressure that I call here, that's P at 0 minus, I could call it. Yeah? So this is what I call P1, to make it simple. So this is P1. And then if I'm just behind my actuator disk, I have P2. So that I call P of 0 plus. So it's just one mini point after the wind turbine. And then I will have my pressure at P3 at the end. P3, which is equal to P at plus infinity in our model, but it needs to be, and that's again something we know already, equal to P0. So this level and that level must be equal in size. So now we have the big picture, what happens around the wind turbine. And from this picture and from this understanding, we want to derive now a limit on how much power we get. So is the notation clear? So we have basically 4 reference points. One is at minus infinity, just in front of the turbine. I call it 0. Then there is 1 and 2, the ones just before and after the turbine. And then 3 is on that side. And 0, by the way, also corresponds to what we would have if there's no wind turbine at all. So now let me just think a bit and collect some things that we know. And at the end we want to discuss what power we will have in the turbine. So the first question is, what is the mass flow through the turbine? I mean, how much air is flowing through the turbine? I think we managed to do that before. I call it m dot, just to give it a name. Yeah, m dot is like the mass that flows through the disk. What is this mass? It's certainly proportional to the density of air, right? So it must be rho. It's certainly proportional to the area of our disk, so it's proportional to A. That's like before. But now, which speed? Because the air is flowing through the disk with a different speed than we thought before. Yes, so let me just say, to be very exact, density would be a bit varying with pressure, right? The variations are so small here that we still regard it as incompressible. Yeah? It would be, for a very refined analysis, this would also be necessary to include. So assume incompressible air. It's a good question, actually. So we assume incompressible air. Like liquids, for example, would be nearly incompressible. I mean, air is obviously not. You could compress it yourself even when you pump up your bike, right? But if you would pump up your bike with water, you could get a very high pressure without any little compression. And so this is, and for wind turbines, their effect is not as strong as what you have in the pump here. So it's like little pressure differences. So we can safely assume one value for rho, which is like the one that we had before. But it's a very good point. Thank you for the question. So we have rho times A, and then there needs to be a speed. But which? Yes?
I just want to ask
A question first.
compressed air is temperature parameter.
Of course, rho depends on temperature and pressure in principle. We will discuss that a bit later also. But we decided now, also because of the scheduling of Rachel's availability and so on, and also because we wanted to have meaningful questions from the beginning, that we start with a bit of turbines, and then we go back to this only matters when you go up, let's say, hundreds of kilometers high, then the density and temperature of air changes significantly. But rho depends on temperature and pressure and temperature, of course, but we neglect that. So we assume incompressible, fixed density. And we basically want to do the same reasoning as before. So we have a wind turbine, there's air flowing through it. You remember how we derived this formula? And so there we had actually multiplied this with the speed, and then we got the mass flow. But which speed do we need to get the right mass flow? U1, you say. Yeah? Anyone says something else? I would accept one other answer. Yes? Okay, yeah, U2 or U1. Perfect, great. Let's just call it U1, and whenever we have a U2, we directly replace it by U1. So that's the mass flow through the turbine. So we know already how much mass flows through the turbine. And now we could just try to collect some quantities and then try to equate them later. So now the question is, what would be the thrust of the turbine? And thrust is a force. That's the force against the wind. Yeah? So how would we say, actually, what would we know about thrust? Thrust, we call it T. And T is, in this case, it's actually a pressure difference times area. That would be one easy way to derive it, right? So it should be the area times the pressure difference. And now let's just look at the numbers. So I want when I write symbols here, I just keep track that they are positive. So you think of the sign. So it's the force against the wind in this direction. So what is this force? It will be actually, so it will be P2 minus P1. Yeah, this difference, P2 minus P1, and then I have a positive number, and this number is actually, if you regard the wind turbine, it's the force that pushes against the tower in that direction. If you regard the wind field, it's the force that pushes the wind field in that direction, because they need to be equal. So this would be the first formula, the thrust of the turbine. But we can also have the same from another perspective, and that would be the perspective of the fluid. I mean, what does the wind turbine do? I mean, if you just look at the top, what it does, it takes air with velocity u0. I mean, all this air that flows through the turbine first had the velocity u0, and then due to this force, it will get slowed down. And slowing down of mass is exactly what we call change of momentum, right? I mean, that's what force is equal to the change of momentum. So we could also, this would be the pressure equation. By pressure, we get this. And now we would, by momentum, by change of momentum, we could get the same. Equivalently, use change of momentum. So let's use change of momentum, and then we also get thrust. So thrust is the mass flow. Yeah, so how much mass gets changed momentum? If there wouldn't be a dot, it would be just momentum. But if you change momentum, then you get a momentum change per time, and that's actually a force. So what we have here is m dot, the same quantity that we have up there. And then we need to, again, have a positive number. So it's actually u0. That's this momentum we had at the beginning, and then it gets slowed down due to this thrust of the wind turbine, and it will have at the end u3. So at the end it will have another speed. And this whole speed change will of course be caused by the pressure differences here. If we look at this picture here, I would like you to get the picture. I mean, the air gets already slowed down before it arrives at the turbine, and that's actually due to this negative pressure gradient here. Right? It's pushing basically in that direction. And then the same thing happens even after the turbine. It gets also slowed down. And at the turbine itself, there's this change where actually the airflow doesn't interact only with other air, but it interacts with the disk itself, and that's why there is this discontinuity possible. Yeah. Yes?
So you said we need a positive number for thrust, but
yes.
P2 minus P1 is the negative.
Sorry, P2 minus... Yes, so that's very good that you say this, and this is very nice. Yeah, so we have P1 minus P2. I want a positive number. Absolutely good. Great, thank you. Maybe just to get a bit of an idea of pressure, think of a balloon, right? If you blow air into a balloon, inside the balloon there will be higher pressure, and then there's this thin boundary at which you get a pressure difference, and that's somehow what we also have here. I mean, the only difference is that our balloon is, so to say, porous. There's always air flowing through it. So you could think of the wind turbine as being maybe, the sieve or a balloon skin, so to say, through which there's always a bit of air flowing. So that's force and thrust. And I want to collect some other equations. And the other equations, first there's a question. Yeah. Yes. Yeah, I mean, in reality, there's always reality and there's this model. Yeah, in reality, of course, it's much more complicated because there's actually air blades going through this thing, so it's time variant even and so on. But what we want to do here is we want to imagine that it's basically an infinitely thin balloon skin, so to say, on a disk, and that the air is blowing through the skin. Yeah? And this skin slows it down, and by slowing it down, it extracts the energy that it takes out. And that's actually what I want to discuss now. So how much energy do we get out? And this is actually the energy that we get out of the flow field. It's independent of losses. I mean, of course, the generator will not be perfect and so on, right? But if you just think of how much air do you get out of the air, there would be also 2 points of view. And the first one is actually from pressure, energy extraction. So let me just collect numbers. So the first one is actually what we do is we have a force that's acting on air that's flowing through our disk with a speed u1. And if you think of what is power is actually force times speed, right? I mean, if you have a strong force against which you, I mean, we didn't use that yet, but force times speed is power, right? So here we actually have a force, and we exert this force on air which flows through our disk with speed u1. And because we slow it down, we will extract actually energy from it. So one way is to just say the power is equal to the thrust times u1. That would be one point of view of what power we extract. Just the force that we have against the wind field. And then the other point of view is from the energy balance. Actually, maybe I should think of this again, because I improvised. This is some equation I need to recheck a bit later. But what I'm sure of is the following. I mean, how much power do we take out? I mean, just think of this thing. I mean, we had air that flows with a velocity u0 at the beginning and u3 at the end. And the same air is actually there at the beginning and at the end. So what we can use is a formula like similar to the one that we had before. By change of kinetic energy. So let's just look at what is the kinetic energy change. I mean, its power is the mass flow, yeah? And then times 1/2 u0 squared minus 1/2 u3 squared. Yeah? That would be the power of our wind turbine. I mean, kinetic energy is mass times 1/2 times velocity squared, and then per second, then we get mass flow, and then we have power. So this formula is definitely right, so I make a box around it. So now we collected a lot of formulas, and I think we are really in a good position to set the stage for the derivation of what we want to do, but we will not arrive there. So maybe I should just end with the question that we need to answer now. So the real question is, what's the value of u1 and u3? So how much does it get slowed down? Yeah? So the questions, u1 and u3, and also, of course, what's p1 and p2? And, we need to determine all of these together. Yeah? These are the unknowns. And what will help us in order to derive them is one extra physical principle that I will not derive now, and that's called Bernoulli's principle, and it's part of one of your questions. So we need Bernoulli in order to get the extra equation that makes us possible to collect everything. But that's basically now the picture, and next time, it's I think next Tuesday, we will finish the extra disk model and derive Betz law. Okay, so thank you. Thanks.